Okay, so okay, so what's going on? Yeah, okay. Fine. Okay, so we're going to continue now. So, yeah, so we computed the derivative of the determinant of the identity last time. That turned out to be the trace, right? So in the sense the derivative of the identity, derivative of the determinant of the identity, that's a linear map from the space of matrices M and R to R. That linear map is given by the trace, okay? So we'll use this fact later when we talk about the Laplacian and divergence. So we'll use this fact later. Okay, so I'd like to go a bit faster now, and quickly we'll try to review integration on manifolds. So we'll talk about integration of differential forms on manifolds. So first we need to do the preliminary linear algebra for that, which is the algebra of alternating forms. So we've talked about multilinear functions, right? So the space of multilinear functions is identified with V star tensor power k. And we say k multilinear function alpha is alternating if whenever you interchange two vectors vi, vj, then alpha changes sign. So that means when you permute by a transposition, the sign changes by -1. So for a general permutation, alpha will change by the sign of the permutation. Okay. So such a form is called an alternating form. So for example, if I take the determinant, I think of it as a function of n column vectors in Rn. So the determinant is an alternating form, right? Okay. So this is the basic example of an alternating form, is the determinant. Okay. So we're going to define this notation, wedge k v star. This will be the space of alternating forms. Okay, so this is a subspace of the space of k multilinear functions. Okay. Now, how do we construct alternating forms? So it turns out there's a projection from the space of k multilinear functions to the subspace of alternating forms called the alt map. So the alt map is the following: alt of k multilinear function omega is another k multilinear function, alt omega, which acting on k vectors v1 to vk is the following. It's 1 over k factorial, sum over permutation sigma in the symmetric group Sk, sine of sigma into omega of the permuted vectors v sigma 1 up to v sigma k. Okay. So actually what we're doing here is the following. If you take the symmetric group, so Sk, this has actually two actions on the space of k multilinear functions by permuting the arguments of the multilinear function. So if I take a sigma dot omega, this will be the k multilinear function whose value on v1 to vk is omega of v sigma 1 to v sigma k. Okay, but actually we have another action, because there are two homomorphisms, right? From the symmetric group into the reals, the non-zero reals, right? One is the trivial homomorphism, and the other is the sign homomorphism, right? So using this homomorphism, we can twist this action and define a second action. So let me call this action with a tilde. So sigma acting on omega for this second action will be sine sigma into omega of V sigma 1, V sigma k. Is this clear? So this will also be an action. All right, so there are two actions actually. And so if I call these actions 1 and 2, then what I'm interested in are fixed points of this action. So fixed points of the first action are exactly symmetric multilinear functions. And fixed points of the second action are exactly alternating multilinear functions, right? Is that clear? Okay. So given a finite group G, how do you get, acting on a vector space, how do you get a fixed point for the action? Well, one way is to take the orbit of any vector and then average over the group, right? Average over the orbit. Take the average of elements in the orbit, then that will be invariant under all group elements because the orbit is invariant under the group, right? So to construct fixed points of the second action, you average over the group. So alt omega is actually just the average over the group. So that's 1 over the order of the group, k factorial, and then sum over the group. So that will give you a sum over the orbit. So sigma dot tilde omega. Okay. This will be by construction a fixed point of the second action. Is this clear? Okay. Which is the space of alternating K forms? Okay. Is this clear? Yes?
Yes.
All right. So that's what we're doing here when we define this alt map. We're just averaging over the group with respect to this twisted action. Okay. So then it's clear that alt omega belongs to the space of alternating forms. And if you start with an alternating form, then it is invariant under this action. So when you average, you'll just get back the form itself. So alt of omega is equal to omega if omega is an alternating form, right? So that means that alt squared is equal to alt, right? So it's an idempotent linear map. So it's a projection, all right, to the space of alternating forms. Is that clear? Yes?
Yes.
Okay, so now we can define using the alt map a product on the space of alternating forms. So if I take a K alternating K form alpha and an alternating K form L form beta, sorry, then we can form an alternating K plus L form alpha wedge beta. So this is defined to be the following. This is K plus L factorial divided by K factorial L factorial into alt of alpha tensor beta. So note that even though alpha beta are alternating, the tensor product is not alternating. Okay. So to get an alternating form, you have to apply alt to it. Okay. So then that will give you a K plus L alternating form. Okay. So this gives you a bilinear product. Okay. Alpha beta goes to alpha wedge beta. And then I won't prove this, but you can see, check that this is associative. Okay, so omega wedge eta, the whole thing wedge theta is the same as omega wedge eta wedge theta. And you can give a formula for this wedge product of three forms. It's given by K plus L plus M factorial divided by K factorial L factorial M factorial into alt of omega tensor eta tensor theta, where K, L, M are the degrees of omega eta theta. Okay. And similarly, for higher order wedge products, you have a similar formula. The wedge product of M forms, alpha 1 to alpha M, will be K1 up to Km sum factorial divided by K1 factorial up to Km factorial product into alt of alpha 1 tensor up to alpha M. Okay. So now, if I take, let's say K1 forms, what happens? So suppose alpha 1 to alpha K are one form. So that means they're just linear functionals. So elements of V star. So then alpha 1 wedge alpha K will be a K form, right? So what is this K form acting on vectors V1 to Vk? So from the above formula, this is K factorial into alt of alpha 1 tensor alpha K acting on V1 to Vk. Now, in the definition of alt, it's an average. So there's a 1 over K factorial that will cancel with this K factorial. So this will just become a sum over the symmetric group sine sigma into alpha 1 of V sigma 1 up to alpha K of V sigma K. Now, this you can see, this is from the definition of determinant. This is the determinant of the following matrix. The matrix whose columns are alpha 1 up to alpha K acting on V1. And then alpha 1 up to alpha K acting on Vk. Right? So what happens is that when you have K1 forms, alpha 1 to alpha K, right, that gives you a linear map T, which is alpha 1 up to alpha K. This is a linear map from V to Rk. Okay. And then alpha 1 wedge alpha K acting on vectors V1 to Vk as we've just seen, this is equal to the determinant of the matrix TV1 up to TVK. Okay. Is this clear? Yes?
Yes, sir.
Okay, fine. So in particular, if you start with a basis E1 to En of V, and you take E1 star up to En star is the dual basis of V star, then if I take E1 star wedge En star, right, then this will just be the determinant of, well, the linear map determined by E1 star up to En star. So this is determinant of what? I mean, if I give you n vectors V1 to Vn, then you express them with respect to the basis E1 to En. That gives you an n by n matrix. You take its determinant, right? Okay. So in that sense, this E1 star wedge En star, this gives you the determinant, which is an element of wedge NV star. Okay. And from this, you can also see that in this wedge product of one forms, the wedge product itself is alternating, acting on one forms. If I permute the one forms alpha 1 up to alpha k, then I'll get the wedge product alpha 1 wedge alpha k times the sign of the permutation, right? Because if I permute the alphas here, that will mean just permuting this matrix, right? So the determinant will change by the sign of the permutation of the alphas. Okay. All right. So the wedge product has this alternating property as well. Okay. Acting on one forms. Okay. And it's also easy to see from this determinant representation that if I take k indices I1 to Ik in strictly increasing order and another k indices J1 to Jk in strictly increasing order, then Ei1 star wedge Eik star acting on Ej1 to Ejk, this is one if and only if all the I1 up to Ik are equal to J1 up to Jk and zero otherwise. Okay, can you see that? Because if I1 to Ik is equal to J1 to Jk, then this matrix becomes the identity matrix. So the determinant is 1. Otherwise, you can see that, let's suppose J1 is less than I1, right? So then all of these Ei1 star up to Eik star acting on Ej1 will give you 0. So the first column of this matrix will become 0. So the determinant will become 0. Okay. So J1 has to be greater than or equal to I1. But if J1 is strictly bigger than I1, then that means all of the J's, J1 up to Jk, are all bigger than I1. Then that means Ei1 star acting on all of the Ej1 to Ejk will become 0. So then that means the first row of this matrix will become 0. So therefore, J1 has to be exactly equal to I1. Okay. And then similarly, after that, you can show that J2 has to equal I2 and so on. Okay. Is that clear? Yes?
Yes, sir.
Okay. All right. Fine. So once you know this, then it's easy to see, like we proved for when we were doing a basis for the space of k multilinear functions. Similarly, we can use this fact here to show that these Ei1 star up to wedge Eik star, where the I1 to Ik are in increasing order, these form a basis for the space of k multilinear functions. Okay. So any alpha, it's equal to the sum over I1 strictly less than Ik, alpha of I1 to Eik into Ei1 star wedge Eik star. Okay. Yeah, so this representation, how do you see this? Well, you just apply both sides to any k tuple of basis vectors in increasing order, Ej1 to Ejk, then both will take the same value on Ej1 up to Ejk by this property here, right? Only one of the terms on the right-hand side will be non-zero. All the other terms will be 0, right? And the only non-zero term will be 1 times alpha of ej1 to ejk, which is the same as the left-hand side, alpha of ej1 to ejk. So these two are alternating forms which take the same value on basis vectors in increasing order, right? K tuples of basis vectors listed in increasing order. But if they take the same value on K tuples in increasing order, then they, because both are alternating, given any K tuple of basis vectors, I can always permute them so that they are listed in increasing order, right? So therefore, if two alternating forms take the same value on basis vectors in increasing order, then they will take the same value on all K tuples of basis vectors. And then, because by multilinearity, they will take the same value on all K tuples of vectors. So they will be equal. All right. Is that clear?
Yeah.
Fine. So therefore, therefore we have this representation. And from this, you can see, therefore, that this EI1 star wedge EIK star, this will form a basis of wedge K V star. Okay. So that means, what will the dimension of wedge K V star be? So we just have to choose K indices out of N. So the dimension will be N choose K. Okay, if K is between 1 and N, and if K is bigger than N, then this will be 0. Okay. Is that all right?
Yes, sir.
Any questions? Okay, fine. So in particular, when I take K equal to N, then the dimension is equal to 1, right? And up to scalar multiples, there's just one alternating form of degree N on an n-dimensional vector space. So it must be the determinant, right? Okay, it must be the determinant. So wedge N V star is just the span of the line span by the determinant. Okay, scalar multiples of the determinant. Okay. Okay. So let me now talk about pullback of multilinear functions. So suppose T is a linear map bit from V to W. So then T star is, you can define this pullback map T star, which goes from K multilinear functions on W to K multilinear functions on V. Okay, so this goes backwards. All right. So this induced map on K multilinear functions is going in the opposite direction. So actually the point is that this Kth tensor product of the dual, this is what's called a contravariant functor, right? So linear maps going from V to W will induce linear maps on the tensor product of the dual in the opposite direction. Okay. All right. So how do you define this pullback? So T star omega acting on vectors V1 to Vk. So this is supposed to be a K multilinear function on V, right? So V1 to Vk are vectors in V. So T will act on these vectors V1 to Vk to give you vectors in W, TV1 to TVk, and then W omega can act on those, right? So T star omega acting on V1 to Vk is defined to be omega acting on TV1 up to TVk. All right. So this is how the pullback is defined. And it's clear that the pullback of an alternating form will be an alternating form. Okay, so pullback gives you a map from alternating K forms on W to alternating K forms on V. All right. Now, what happens when you pull back an N form? So suppose T is a linear map from V to itself, where V has dimension N, and E1 to En is a basis of V. And so we have one alternating n form, which is the determinant, which is E1 star wedge En star. Okay. So now if I pull back this determinant by t, so t star of the determinant, this will be a constant multiple c times the determinant, because the space of alternating n forms is one-dimensional. Okay, so now how do I get this constant c? Well, I evaluate both sides on the basis vectors E1 to En, right? So t star det of E1 to En will be c times det of E1 to En. And the determinant of E1 to En with respect to the basis E1 to En is just the determinant of the identity matrix, which is 1. So this will give you c. So c is equal to t star det of E1 to En. In other words, this left-hand side becomes det of TE1 TEN equal to c. And this determinant is just the determinant of the matrix, the linear, the determinant of the matrix of the linear map T with respect to the basis E1 to En, right? So that means that C is equal to the determinant of T. Is that clear? Okay. Yes, what is this det acting on TE1 to TEN? That means you take the matrix, you express each of these vectors TE1 to TEN with respect to the basis E1 to En. That gives you a matrix. That matrix by definition is the matrix of the linear map T with respect to the basis E1 to En, right? Then you take its determinant. So that is by definition the determinant of T, right? The linear map T. Is this clear? Okay. So therefore, T star, it pulls back the determinant to determinant of T into the determinant. Okay. So therefore, now since the determinant here, det is a basis for the space of alternating n forms, that means for any alternating n form omega, T star omega is equal to det T into omega. All right. Is that clear? Okay, so actually what is happening, this wedge n V star, this is a one-dimensional vector space, right? So I have a linear map T star pull back from wedge n V star to itself. So this must be multiplication by a scalar, right? This must be multiplication by a scalar, right? Because it's a linear map from a one-dimensional vector space to itself. So it must be multiplication by a scalar, right? So that scalar is nothing but the determinant of T. So in fact, this gives you an abstract way to define the determinant, if you like. The determinant is the unique scalar, so that pullback acting on alternating n forms is given by multiplication by that scalar. Okay, so this is a basis-free definition of the determinant, if you like. All right. Is that clear?
Yeah, it's clear.
Okay, fine. Okay, so now we need to define, for integration, this will be important, what's called orientation. So orientation is the following. So it is an equivalence relation on the space of ordered basis of my vector space V. So if V1 to Vn and W1 to Wn are two ordered bases of V, then we say that V1 to Vn is equivalent to W1 to Wn if the determinant of T is positive, where T is the unique linear map from V to V, which sends the first ordered basis Vi to the second ordered basis Wi. All right. So then you say that these two are equivalent. Okay. So actually, geometrically, what does this equivalence relation mean? What happens is, if I look at the space of ordered bases, so if I look at the set B is equal to the set of ordered bases of V, right, then GLV has a natural action on this set of ordered bases, right? Yes. So, I mean, it's just the obvious action. G dot V1 to Vk is GV1 up to GVK, right? This is a new ordered basis. Yes. Okay. Now, this action is what is called simply transitive, right? Given any two ordered bases, there is a linear map which takes the first ordered basis to the second ordered basis. And moreover, that linear map is unique. So therefore, this action is simply transitive, right? For any two elements in this set, there is a unique group element which takes the first element of the set to the second element, right? So this is a simply transitive action. Okay. All right. So that means what happens is, actually, if I fix, say, an ordered basis, say, what should I call it? I don't know. So fix V1 to Vk in my set of ordered bases. So then the map, the orbit map, GLV goes to B, G goes to G dot V1 to Vn. This is an N here, sorry, not a K. This map is a bijection, right? This map is 1-to-1 on 2. Okay. And actually, you can think of, if you put the appropriate topology on the set of ordered bases, the set of ordered bases is identified with V power n, right? And V is a finite dimensional real vector space. There's a natural topology on it once you identify it with Rn, right? Coming from any norm on it. All norms are equivalent. So there's a canonical topology. And so this set of ordered bases is identified with V power n, that's has a canonical topology. So this map is actually a homeomorphism. Okay, this is actually a homeomorphism. So this set of ordered bases, this is homeomorphic to the general linear group GLV. Okay, and what is an orientation? Well, what happens is actually that GLV has two connected components. The set of matrices with positive determinant union the set of matrices with negative determinant. These are the two connected components. And an orientation is nothing but a choice of connected component. Okay, after you identify the set of ordered bases with GLV. Okay, so let me stop this meeting and start another one. We've got less than 1 minute. So let me stop and start a new meeting. Okay. Okay, so let's start. Yeah, so we've seen that this set of ordered bases this is identified with GLV as a topological space, and GLV has two connected components. The set of matrices with positive determinant and the set of matrices with negative determinant. Okay, you can try and show that these are actually the two connected components of GLV. And what we're doing is an orientation on V is equal to a choice of connected component of the set of ordered bases. Okay, so an orientation is defined to be an equivalence class, right? We define this equivalence relation on the set of ordered bases. Two ordered bases are equivalent if the determinant of the unique linear map taking the first ordered basis to the second ordered basis, this determinant is positive. So an orientation is an equivalence class of ordered bases. So that will correspond to, under the identification of the set of ordered bases with GLV, that will correspond to either GL plus V or GL minus V, right? Okay. So it's a choice of connected component of the set of ordered bases. So you can see this in two dimensions easily. So in two dimensions, what happens? So if I have two ordered bases, say V1, V2, and W1, W2, say in R2, then I can deform the first ordered basis into the second ordered basis, right? So let me fix the standard basis, let's say. So as V1, V2 is, say, the standard basis. Okay. Say E1, E2. So this angle is 90 degrees anti-clockwise. So I can deform this basis into this basis if and only if this anti-clockwise angle from W1 to W2 is in between 0 and pi, right? Okay. So E1, E2 is equivalent to W1, W2 if and only if theta belongs to 0 pi, right? If the angle is bigger than pi, so W1, W2, if it looks like this, so this is the case where theta is bigger than pi, then I cannot deform this basis continuously into this basis, right? Because intuitively speaking, at some point, when the angle has to become equal to pi, right? The angle is 90 degrees here. Here it's bigger than 180 degrees. At some point, it has to be equal to pi, but then the two vectors will become linearly independent. That's a contradiction, right? Okay. Is this clear? Yes?
Yeah, it's clear.
Okay. So an orientation is a choice of connected component of the space of ordered bases. All right. That is one way you can think of what an orientation is. So two ordered bases are equivalent if and only if I can deform one continuously into the other. Right. If and only if I can deform one continuously into the other. See, the point is the space of ordered bases, that's that's an open subset of V power n, right? Sorry. That's an open subset of V power n, right? So, so it's an open subset of some Euclidean space. Connected component is the same as a path component, right? So an open subset of Euclidean space is connected if and only if it is path connected. So if it's path connected, that means in the space of ordered basis, there is a path, a continuous path from one to the other. That means you can continuously deform one ordered basis into the other. All right. Is that clear? Okay. All right. So fine. So now what? Yeah. Okay. So let's come back to this. Okay. So so on any finite dimensional vector space V, there are just two possible orientations, right? So if I take the equivalence class corresponding to one ordered basis V1 to Vn, then the other orientation, let me call it mu op, the opposite orientation, is just given by interchanging the first two basis vectors. Okay. So is that clear? All right. So there are just two possible orientations, mu and mu op, on any n-dimensional vector space V. And any non-zero alternating form omega, it defines an orientation mu sub omega. This is the set of ordered bases V1 to Vn such that omega of V1 to Vn is positive. So why is this an orientation? Because if I take two ordered bases V1 to Vn and W1 to Wn, and if I let T be the unique linear map which takes Vi to Wi, then what is omega of W1 to Wn? This is omega of TV1 up to TVn. That by definition is T star omega acting on V1 to Vn. And T star omega, this is det T into omega of V1 to Vn, right? Okay. So if V1 to Vn belongs to this set mu omega, that means omega of V1 to Vn is positive, then W1 to Wn will also belong to mu omega. That means omega of W1 to Wn will be positive if and only if determinant T is positive. That is, if and only if V1 to Vn is equivalent to W1 to Wn. So that means that this mu omega, this is an equivalence class, right? So therefore it is an orientation. Is this clear? Yes?
Yes, sir, it's clear.
Okay, fine. So now I want to define a special n form which you get when you have an oriented inner product space. Okay, so this will allow us to integrate on Riemannian manifolds. So, so what do we have? We have V is an inner product space together with an orientation mu. Okay. All right. So we have an inner product and an orientation. Then we can define what's called the volume form of V, dvol. So this is going to be an n form defined to be E1 star wedge En star, where E1 to En is any orthonormal basis of V which belongs to this orientation. Okay, so we call it a positively oriented orthonormal basis. It's an orthonormal basis which belongs to the given orientation, right? Remember, an orientation is an equivalence class of ordered bases. So it's a set of ordered bases, right? So we're taking any orthonormal basis which belongs to this orientation, this set of ordered bases. Okay. Then the claim is that this E1 star wedge En star, this is independent of the choice of positively oriented orthonormal bases. Okay. So why is this? Because if I take any other positively oriented orthonormal basis F1 to Fn, then if I let T be the linear map which takes the first orthonormal basis EI to the second orthonormal basis Fi, then since it takes orthonormal basis to orthonormal basis, it is an orthogonal linear transformation of V. And since EIs and FIs are both in the same orientation, the determinant of T by definition is positive, but the determinant of an orthogonal transformation is plus minus 1. So if the determinant is positive, it has to be equal to 1. So the determinant of T is 1. So then if I look at my n-form d-vol acting on F1 to Fn, well, F1 to Fn I can write as T of E1 up to T of En. So then this becomes, by definition, the pullback T star d-vol acting on E1 to En. But T star d-vol is the determinant of T into d-vol of E1 to En. And the determinant of T is 1. And d-vol of E1 to En by definition is 1. Because d-vol is E1 star wedge En star. So this becomes 1. So that means d-vol acting on F1 to Fn is 1. But also, if I look at F1 star wedge Fn star, this acting on F1 to Fn, this is also 1, right? So therefore, my two n-forms, d-vol and F1 star wedge Fn star, they take the same value, plus 1, on this ordered basis F1 to Fn. And then because they're alternating n-forms, that means they must be equal, right? If they take the same value on some ordered basis, then by the alternating property, they will take the same value on any ordered basis, and therefore on any n-tuple of vectors. So they will be equal. So therefore, d-vol is equal to F1 star wedge Fn star. Is this okay? Yes?
Yes, sir, it's fine.
Yeah. So, the volume form is characterized as the unique n form, which takes the value plus 1 on every positively oriented orthonormal basis. Is that clear?
Yeah.
Right. It's characterized as the unique n form, which takes the value plus 1 on every positively oriented orthonormal basis. Okay. So intuitively, what is happening? An alternating n form gives you a way of measuring n-dimensional volumes of parallelepipeds in your vector space together with a sign. The sign is given by whether the vectors forming the parallelepiped form a positively oriented basis or a negatively oriented orthonormal or a negatively oriented basis. And then the volume form is 1. The way of measuring volume, which gives the value plus 1 to every cube. Every cube has formed by a positively oriented basis has volume 1, okay, with respect to the volume form. Does that make sense? Yeah. Cube will be a parallelepiped formed by an orthonormal basis, right? Okay. All right. Any questions? Yeah, any questions? Yes, no?
So if you take any orthogonal basis and take the wedge product of those, then you get the volume form, right? So
No, it has to be positively oriented.
okay, yeah.
If it's negatively oriented, you'll get minus the volume form.
Yeah, okay.
Yeah. So if you take any positively oriented volume form, that's what we, positively oriented orthonormal basis, then the wedge product of their corresponding dual basis, right, that will give you the volume form.
Yeah.
The wedge product of the corresponding dual basis, right, that will give the volume form. That's what we showed here, right? This E1 star wedge En star, this is equal to F1 star wedge Fn star, right?
Yes, yes.
That's what we've shown here. Okay. Okay, so now we can come to manifolds. This finishes the linear algebra preliminaries. So I suppose you all know the definition of manifold. Do I need to go over that? I mean, I've written the definition here. You have a second countable Hausdorff space together with a family of pairs ui, fi, where the ui's are an open cover of M and the phi i's are homeomorphisms from the open subsets ui to open subsets of Rn. And if I take two sets in this open cover which intersect, ui intersect uj, then you have this so-called change of charts map, phi j compose phi I inverse. That goes from an open subset of Rn to an open subset of Rn. Those maps should be C infinity diffeomorphisms. Okay. So this is the definition of a manifold of dimension n. These pairs ui phi i's are called charts on M. Using the charts, you can talk about smooth functions on your manifold. So the idea is if I have a function on an open subset of my manifold, then using the charts which identify the manifold locally with Rn, my function locally becomes a function on Rn. That function on Rn should be smooth function, right? So formally that means that f composed with phi I inverse, that is a function defined on an open subset of Rn, that should be smooth for all charts, okay? And similarly, if I have two manifolds, Mn, then if I have a continuous map from M to N, then you'll say it is smooth if whenever I take a point P in the domain M and I look at its image point Q in the range N, then if U psi 1 is a chart near P and V psi 2 is a chart near Q, then since the map phi is continuous, I can assume that my chart U is chosen small enough so that phi of U is contained in V. Okay, because phi is continuous, I can choose this neighborhood U small enough so that its image is contained in the neighborhood V of Q. Then I can look at the composition psi 2 phi psi 1 inverse. So then my map between the two manifolds becomes a map between open subsets of Euclidean space from Rn to Rn. This map should be smooth. Okay, so then we say that the map phi between the two manifolds is smooth. Okay, so we can talk about smooth functions on manifolds and smooth maps between manifolds. And then we can also talk about, for any open set U in M, we can define a ring C infinity U, which is the ring of smooth functions on U. Okay, so the sum and product of smooth functions is smooth. And in fact, this is what's called in R algebra, this because you have a scalar multiplication also, which commutes with the ring multiplication. Okay, so this is a vector space over R, which with a bilinear product, which commutes with scalar multiplication. So this is in fact an R algebra. Okay, the algebra of smooth functions. Okay, and what I want to talk about, which may or may not be familiar to all of you, is the definition of tangent space at a point of a manifold. Okay, so let me just explain this a little bit before getting to the definition. So if I have a manifold, right, so suppose S2 sitting inside R3, so if your manifold sits inside some Euclidean space, then the tangent space at a point is easy to define. So if I take this point here, right, so I have some neighborhood. I have a chart from this neighborhood to a disk in R2, right? So some disk D inside R2. So this is my chart phi, and then I can look at the inverse of this chart, right? So phi inverse, this goes from an open set in R2 into R3. Well, it's going into S2 inside R3. Okay, and this map, it turns out, actually is smooth. Okay, this map is smooth. So I can look at its derivative. So say d phi inverse at a, so if this is P and the image point is Q, then I can look at d phi inverse at Q. That will go from R2 to R3, right? Because this is a map from an open subset of R2 into R3. So the derivative goes from R2 to R3. It's a linear map. And so what should the tangent space be? The tangent space should be the image of this linear map, right? That will be a two-dimensional subspace of R2, which you imagine as tangent to the sphere, right? So you can define TP_S2 in this case to be the image of d phi inverse at Q. So this is a subspace of R3, a two-dimensional subspace, right? So if your manifold is sitting inside some Euclidean space, then you can define the tangent space very concretely using the charts, right? You take the inverse of the chart, you take its derivative, you take the image of the derivative, okay, of the inverse of the chart. That will give you an n-dimensional subspace of your Euclidean space where your manifold is sitting, which you can think of as the tangent space at that point, right? But this a priori, it depends on an embedding of your manifold into some Euclidean space, right? But in general, manifolds don't come with any preferred embedding into Euclidean space. For example, if you take the torus R2 mod Z2, it's a quotient space, right? It's not sitting naturally embedded into any Rn, right? So manifolds often arise as quotients of spaces by group actions, for example. So those don't come with any embeddings, any natural embeddings into Euclidean space. So one wants a definition of the tangent space which is intrinsic, okay, which doesn't depend on any embedding. And the idea to define the tangent space then is the following. So you have some point, say P in your manifold, okay, and the idea is that tangent vectors at P. So if this is a tangent vector, so, well, the idea is a tangent vector should give you a direction in which you can differentiate functions defined near P. Okay. So now derivative of a function only depends on the function in a neighborhood of the point, right? So therefore we should consider functions up to an equivalence where you identify two functions if they agree in a neighborhood of P. Okay, so this leads to the definition of what's called the space of germs of smooth functions. So if a point P in M is given, then you define the ring of germs of smooth functions at P. This is defined to be the ring C infinity M comma P. This is given by pairs U comma F, where U is an open neighborhood of P and F is a smooth function on U, modulo the equivalence where two pairs U comma F and V comma G are identified if there exists an open subset W contained in the intersection of U and V, and W is an open neighborhood of P, such that F restricted to W is equal to G restricted to W. Okay, so you're identifying two functions defined in a neighborhood of P if they agree in some smaller neighborhood of P. Okay. So this defines for you the set of germs of smooth functions, and then it's easy to see that you can add germs and multiply germs. Okay, so addition and multiplication of functions is compatible with this equivalence relation. So you get addition and multiplication on the quotient by this equivalence relation. So this space of germs becomes a ring, okay, and also in R algebra. Okay. So you get this ring of germs of smooth functions at a point P. And now, algebraically, what is a derivative? So a derivative is something which satisfies the Leibniz rule, right? So, so we define the tangent space to the manifold M at a point P, TPM. This is the following. It's the set of linear maps D from the ring of germs of smooth functions at P to R, such that D is linear and satisfies this following Leibniz rule at P. So whenever I take two germs F and G of smooth functions at P, then D applied to F times G should be D applied to F into G of P plus F at P into D of G. Okay, so this is the algebraic way of capturing what is a derivative. It's just something which satisfies the Leibniz rule. Okay. Now, what do we want? We want that this tangent space to an n-dimensional manifold should be an n-dimensional vector space, right? Now, it's easy to see that the ring of germs of smooth functions, that is an infinite dimensional vector space, right? At any point P, you can just take germs of polynomial functions near P, where, polynomial functions with respect to some chart, right? So those will give you an infinite dimensional subspace of your space of germs. So the vector space of germs is infinite dimensional. So if I just looked at linear maps on the space of germs, that would be the dual of an infinite dimensional vector space. That would be infinite dimensional. So just looking at linear maps is not enough, right? I want a finite dimensional vector space. What happens is when you apply this extra condition, this Leibniz rule, that magically brings down the dimension to exactly n. Okay, so requiring this Leibniz rule is what will give you a finite dimensional vector space of dimension exactly equal to the dimension of the manifold. Okay, so we're going to see how this works out. So first of all, suppose I take a chart u comma phi near a point P. So phi is given by functions x1 to xn. It's a map from u into Rn. So x1 to xn are the coordinates, the components of phi. Okay, they're smooth functions on u. So let q be equal to phi of P. Then we can define certain elements of this tangent space. So those are going to be, so these linear maps which satisfy the Leibniz rule at P, these are called derivations at P. Okay, these are called derivations at P. So we can define certain derivations at P, del xi at P. These are going to be elements of the tangent space. So how are these defined? So del xi at P acting on a germ of smooth function f is the following. So f is defined in a neighborhood of P. It's a smooth function in a neighborhood of P. So I can look at f composed with phi inverse. That will be by definition a smooth function in a neighborhood of Q in Rn, right? Then I can take its ith partial derivative del xi of f composed phi inverse. I look at the value of this at Q. So then it's easy to see by the one variable Leibniz rule that this del xi, this is going to satisfy the Leibniz rule at P, right? Is that clear? Yes. Okay. So this is going to define for me an element of the tangent space at each point P. Is this clear? Yeah.
Yeah, it's clear.
Okay, fine. So basically, what is it? See, once I have coordinates near P, then F becomes a smooth function of the coordinates, right? F becomes some function of x1 to xn. And then I'm just taking the usual ith partial derivative of F with respect to xi, right? That's all. Okay. That's all. Okay, so yeah. So what we're going to show is actually these del xi's, these form a basis for the tangent space. Therefore, the tangent space is n-dimensional. Okay. But before doing that, let me give you another example of tangent vectors. Suppose gamma is a smooth curve in M. Okay. So what is a smooth curve? It's a map from an interval into M, such that when I compose with any chart, phi composed gamma will be a smooth curve in Rn for any chart phi. Okay. That's what it means to be a smooth curve in M. Okay. Then if I take a T naught in the interval of definition of phi of gamma, then I can define a tangent vector to the curve gamma prime T naught. This is going to be an element of the tangent space at gamma T naught. So how is this defined? So gamma prime T naught acting on a germ of smooth function F near gamma T naught. This is defined to be nothing but ddt at t equal to 0 of f of gamma t, right? Okay, the point is because gamma is a smooth curve in M and f is a smooth function on M, f composed gamma will be a smooth function of t of one variable. All right? Because I can write this f composed gamma as f composed phi inverse composed phi composed gamma. And f composed phi inverse is a smooth function on Rn. And phi composed gamma is a smooth curve in Rn. Therefore, the composition will be a smooth function of t. Is that clear? Yes?
Yeah,
Yes.
yeah, it's clear. Yeah, it's clear.
Right. I just write this, put a phi inverse and a phi in between this f and gamma. That's all. Then you can see it becomes a smooth function in Rn composed with a smooth curve in Rn. So it's a smooth function of one real variable. Okay. And by the Leibniz rule for one variable functions, this will satisfy the Leibniz rule at P. Right. So therefore, this will define an element of the tangent space. Is this clear? Yeah. Okay, so this by definition is defined to be the tangent vector to the curve gamma at a point gamma T naught. Okay. All right. Now let's come back to this set of partial derivatives, these del xi's. So it's easy to see these del xi's are linearly independent because what is del xi acting on a coordinate function xj? This is just going to be delta ij, right? Yes? Right?
Yeah.
Delta xi acting on xj will just be delta ij. So therefore, if I have a linear combination, summation alpha I del xi at p equal to 0, then I just apply this linear combination to xj. Then all the terms will drop out except for the jth term, and then I'll get alpha j into 1. So that will give me that alpha j is equal to 0. And this is true for all j. So therefore, all the alpha i's are 0. So therefore, this set del x1 up to del xn is linearly independent. Okay? Is this clear? Yes?
Yeah, it's clear. Yeah.
Okay. So I've got a linearly independent set. Now all I have to show is that they span, right? Then I'll get that it's a basis. Okay. So I just have to show that these del xi span the tangent space. Okay. So now suppose D is an element of the tangent space. So it's a derivation at P. So by the Leibniz rule, what happens to the constant function 1? So 1 is equal to 1 times 1. So d of 1 will be d of 1 times 1. By the Leibniz rule, this will be 2 times d of 1, right? Because it's 1 into d of 1 plus d of 1 into 1, right? So this will give me 2 times d of 1. So therefore, d1 is equal to 2 times d1. Therefore, d of 1 is 0. So d maps, any tangent vector maps the constant function 1 to 0. That's what you would expect, right? A tangent vector is a way of differentiating. So it should give the value 0 applied to any constant function, right? Okay. So yeah, so it gives the value 0 applied to the constant function 1. And then by linearity, if I take any constant function alpha, then d of alpha will be alpha times d of 1. So that will be 0. Okay. So therefore, d vanishes on any constant, on all the constant functions. Okay. Now, we can also do the following. So on this ring of germs of smooth functions at P, I have this evaluation homomorphism at P. A germ F goes to its value at P, F of P. So this is a ring homomorphism from the ring of germs to the real line. And it's a surjective ring homomorphism, since for any real number alpha, you just take the constant function alpha. So this is a surjective ring homomorphism. So its kernel, which is the set of functions vanishing at P, that will be a maximal ideal, right? Okay. So this maximal ideal, let's call this M sub P. Okay. And it turns out it's easy to see this, that this is the unique maximal ideal of this ring. In other words, this ring is a local ring. It has a unique maximal ideal, right? Because if you take anything outside the maximal ideal, it will become invertible. Because if it's outside the maximal ideal, that means f of p is non-zero. So if a function is non-zero at p, then by continuity, it's non-zero in a neighborhood of p. Then in that neighborhood, 1 over f is also a smooth function, and it gives you an inverse, right? In the ring, in the space of germs. Right, to define a germ, I just need a function defined in a neighborhood of P. It doesn't have to be defined globally, right? It just has to be defined locally. So if I take anything outside the maximal ideal, it does not vanish at P. Therefore, it has a local inverse 1 over F. That gives you an inverse in the ring of germs. So therefore, anything outside the maximal ideal is invertible. So this is the unique maximal ideal. Okay. All right. Yeah. So this ring of germs, I mean, germs are local objects, as you would, as one would hope. I mean, this ring of germs should be a local ring, right? So, in fact, this is the motivation for defining local rings. It came from these rings of germs. Okay, let me stop here and start another session, okay? We've got less than a minute, so. Okay. Yeah, fine. So we have this unique maximal ideal of functions vanishing at P in the ring of germs of smooth functions at P. Now notice, if I have two functions f and g in this maximal ideal MP, then what is d of f times g going to be? Well, this is by the Leibniz rule, d of f into g of p plus f of p into d of g. But gp is 0 and f of p is 0. So this becomes 0. So therefore, d of fg is 0 for all fg in the maximal ideal. That means that d vanishes on the square of the maximal ideal, right? So d vanishes on MP squared. Is that clear? Okay. And d vanishes on the constants. All right. Yes.
Yeah.
Okay, look, d vanishing on the square of the maximal ideal should be intuitively clear, because things in the square of the maximal ideal, those are products of functions which vanish at P. So look, if you vanish at P and you're a smooth function, then you should be of first order near P, right? And if you take a product of two functions which are of first order near P, then the product will be of second order, right? So something which is of second order, which vanishes up to second order at P, its derivative at P will be 0, right? In any direction. So therefore, any tangent vector, intuitively, it should vanish on the square of the maximal ideal. Okay. So that's what we get just by looking at the Leibniz rule. All right. So using this, now we can show that the del del xi's span the tangent space as follows. So take a function f which is a germ of smooth function near P. Look at the corresponding function in Rn. So look at f tilde, which is f composed with phi inverse. Okay. So this is a germ of smooth function in Rn near Q, where Q is phi of P. Now, if I take any x which is near Q by the fundamental theorem of calculus, I can write f tilde of x as f tilde of Q plus the integral from 0 to 1 of d dt of f tilde of Q plus t times x minus Q dt, right? This is just the fundamental theorem of calculus. Okay. Yes. And now let me look at this derivative. By the chain rule, this will be what? This will be the sum over I del f tilde del xi at this Q plus tx minus Q into the derivative of this curve. T goes to Q plus tx minus Q. The derivative of this curve is constant, equal to x minus Q, right? So what will I get? I'll get, so what I get is a summation over I del f tilde del xi at Q plus t into x minus Q. So what I'll do is I'll subtract the value of del f tilde del xi at Q and add also the value of del f tilde del xi at Q. So I'll just add and subtract this del f tilde del xi at Q. Then I break up the sum into these two terms. So the first one, I'll have sum over I del f tilde del xi at Q into xi minus qi dt. Okay. So this is independent of t. And then the other term will be the following, sum over I. I'll have this xi minus qi into integral from 0 to 1 del f tilde del xi at Q plus t into x minus Q minus del f tilde del xi at Q, whole thing dt. Okay. Is this second line all right? Yeah. Yeah. So now this first term here, this integral doesn't depend on t, so it just becomes this. Okay. And so what is this del f tilde del xi at Q? This by definition is the tangent vector del del xi at P acting on f, right? Okay. That into xi minus, this should be qi. There's a typo here. This should be qi. And plus sum over I. Again, there's a typo here. This should be qi. Xi minus qi into, so this function here, this is a function of x, this integral, this is a function of x. So I'm going to call this g tilde, there should be an I here, gi tilde of x. Okay. So now if we put x equal to phi of some y, so x was a point in Rn near Q, which was phi of P. So x is going to be of the form phi of y, where y belongs to a neighborhood U of P. Okay. So then f tilde of x is just going to be f of y. So this becomes f tilde Q is just f of P plus sum over I del del xi at P applied to f into this xi becomes xi of y minus this qi becomes xi of P. So you get xi y minus xi P plus the sum. Now I have xi minus qi here. This is xi y minus xi P into, I get gi tilde of phi of y, right? X is equal to phi of y. This becomes gi tilde of phi of y. Okay. Now, what is the point? The point is the first term here, f of p, this is a constant, right? And this last term here, this function, xi of y minus xi of p, as a function of y, this vanishes at y equal to p, right? This vanishes at y equal to p. So this belongs to the maximal ideal MP. And this second term here, gi tilde of phi of y, this also vanishes at p because gi tilde of q is equal to 0. Right? Over here in this integral, if I put x equal to q, then this integral vanishes, right? Yes. So this integral vanishes. So that means gi tilde of q is equal to 0. So gi tilde of phi of p will be 0, right? So this vanishes at p. So this last term is a sum of products of elements of the maximal ideal. So this last term belongs to MP squared. So therefore, what have we done? Given any smooth function f near p, we've written it as a constant plus this linear combination of the coordinate functions minus the value at p into coefficients which are del del xi's acting on f plus something in the square of the maximal ideal. Therefore, now if I take any tangent vector d, if I apply d to f, then d is going to vanish on the constant part and it's going to vanish on the part which is in the square of the maximal ideal. What's going to remain is just d acting on this part in the middle, right? So this del f del xi, these are constants and d is linear. So this is going to become d acting on these functions, right? And this xi of p is a constant. So it'll just be d acting on xi, right? So what you'll get finally is that d acting on f is the sum over I, d acting on xi times del del xi at p acting on f. Is this clear?
Yeah, it's clear.
Right. Okay. But what does this mean? This is true for all f, right? And this left-hand side, the right-hand side is a linear combination of the del del xi's with coefficients d of xi's. This linear combination acting on f, right? So this is true for all f in the ring of germs. What does that mean? That means that d is equal to this linear combination, sum over I, d of xi, del del xi at p. Is that clear? Yes?
Yeah, it is clear.
Right, okay. Okay, so therefore the del del xi's span the tangent space, right? And we have not just that, we have an explicit representation of any tangent vector d as a linear combination of the del del xi's. The coefficient of del del xi is the tangent vector d acting on the coordinate function xi. Okay. Is this all right? Yeah. Okay. Okay, so we've got what we wanted. Now we have at each point P, we have an intrinsically defined vector space of dimension n, the tangent space at P. Okay. So this is intrinsic because it only depended on this ring of germs of smooth functions. So that is defined independent of any embedding into Rm, right? It's defined just using the charts on M. So it doesn't depend on any embedding. It's just defined using the notion of smooth function near P. Okay. Okay, good. So once we've got the tangent spaces, we can form a new manifold from the union of all the tangent spaces, which will be important for us. This is called the tangent bundle. So Tm, this is defined to be the disjoint union over P and M of the tangent spaces TPM. Okay. There is a natural projection pi from the tangent bundle Tm to the manifold M, where this projection maps each tangent space TPM to the singleton P. Okay, so I mean tangent vectors based at TPM map to P. Okay, so each tangent vector goes to the point at which it is based. That's all. And it will be convenient to write elements of the tangent bundle as pairs P comma V, where P is a point of M and V is an element of TPM. Okay, so we'll write elements of TM as pairs P comma V. All right. Now we can make this tangent bundle into a manifold of dimension 2n. So how do we do this? So if I have a chart U comma phi, then I can define a chart on this tangent bundle, capital phi. So where will this go? So this will go from pi inverse of U. This is a subset of Tm. So pi inverse of U means all tangent vectors whose projection lies in U. So that means tangent vectors based at points P and U. Okay, so these will be pairs of the form P comma. So since phi is a chart on U, I know that del del xi is at P. These form a basis for TPM. So any tangent vector I can write as summation ai del del xi at P, right? Okay, so these will be pairs of the form P comma summation ai del del xi at P, where P belongs to U. Okay. And then what is my map? My chart capital phi will take values in R2n. It's going to go to phi of U cross Rn, which is sitting inside R2n. So this maps to the pair phi of P, comma, A1 up to An. Okay. So this is my map. All right. So in order to get a manifold structure on the tangent bundle, what I want to do is look at the change of charts. Okay. So on the tangent bundle and check that that change of charts is smooth. All right. So let me take another set of coordinates, say psi equal to y1 to yn. Say, suppose this is another chart on U. All right. Then, first of all, I'll get another basis of the tangent space at each point, del del yj, right? But now I know that del del yj I can express in terms of the old basis del del xi, right? So I use this formula. Any tangent vector d is equal to sum over I d of xi del del xi at P, right? This gives me a way to express any tangent vector in terms of the basis del del xi. So if I apply this formula with d equal to del del yj, then del del yj at P becomes sum over I del del yj at P acting on xi into del del xi at P. Now this xi's are smooth functions. So del del yj acting on xi, this will be some smooth function aij of P. All right. So I get this linear combination sum over I aij of P del del xi at P. All right. Okay. So now, corresponding to this coordinates y1 to yn, I have another chart capital psi on the tangent bundle, right? What does it do? So capital psi acting on P, comma Well, I write a tangent vector in the form sum over j, bj, del yj at p, right? So this is going to map to psi of p, comma, b1 to bn, right? By definition. Yeah. And psi and phi, little psi and little phi, these are charts on M. So the change of chart psi composed phi inverse is some smooth map, some smooth diffeomorphism from Rn to Rn F, right? So psi is equal to F composed with phi, okay? So this I can write as F composed phi p, comma, B1 to Bn. Now I want to see what does capital phi map this element of the tangent bundle to. So what I do is I write my tangent vector v. This is sum over j, bj, del yj at p. I write this in terms of the basis del xi. How do I do that? Well, each del yj I've written in terms of the basis del xi. It's sum over I, aij, p, del xi at p. So I substitute that here. So I get a sum over j, sum over I, bj, aij at p, del xi at p. Now I interchange the order of summation. I take the I outside. So this becomes a sum over I, and inside I get a sum over j, aij p into bj into del xi at p. Okay. So once I've written v in terms of the basis del xi, then I know what my capital phi of p comma v is, right? Capital phi of p comma v is going to be little phi of p together with a1 to an, which are the coefficients of my vector v with respect to the basis del xi. But the coefficients of my vector v are these sum over j, aij p into bj. Now this you can see, this is nothing but these are the entries of the matrix aij into the column vector bj, right? This is just a matrix multiplication, right? Yeah. Okay. So, so what does that mean? That means that capital phi of p comma v is going to be phi of p comma capital A of p into b, where capital A of p is the matrix aij of p, the matrix with entries aij of p, right? So this is a smooth matrix valued function, right? Is this clear? So if I call x equal to psi of p, right, then what is psi inverse of x comma b? That is going to be my p comma v. And then phi of that, phi of p comma v is phi of p comma a of p into b. So that's going to be phi of psi inverse x, right? P is psi inverse x into a of psi inverse x into b, right? So this is a map from R2n to R2n. And the first n coordinates is a smooth function of x, phi composed psi inverse of x. And the last n coordinates, that's a smooth function of x and b. Because this matrix A is a smooth function, a smooth matrix valued function, right? Is this clear? Okay, so maybe I should just write this. All right. So see, I have P in U, and I have a vector V in TPM. So I'm writing V as in two ways. One as a summation over I, AI, del xi at P. And I'm also writing it as sum over I, sum over j, bj, del del yj at p, right? And these AIs I'm getting, AI is equal to sum over j, aij of p into bj, right? Okay, so that means the column vector a1 to an is equal to the matrix A of p into the column vector b1 to bn, right? Where A of p is the matrix aij of p. Right, where aij of p is del del yj at p of xi. Is this clear? Yes?
Yeah.
So what am I doing now? I have my map capital psi. So capital psi of p comma v is going to be what? Is going to be little psi of x comma b1 to bn, right? By definition, yes? Capital psi of p, sorry, capital psi of p. Okay. So let me call capital psi of p is x, okay? A point in Rn. And this b is a column vector in Rn, okay? X is equal to little psi of p in Rn. Okay, b is also a vector in Rn. Okay, so now from this I get that p comma v is equal to capital psi inverse of x comma b, right? So if I apply phi to both sides, I get that phi of capital psi inverse of x comma b is equal to phi of p comma v, and phi of p comma v by definition this is little phi of p comma, so I write v with respect to the basis del del xi's, then this goes to a1 to an, right? Okay, so this I can write further as phi of, so p is psi inverse of x, so this becomes phi composed psi inverse of x, and a1 to an, this becomes the matrix A of p into the vector b. Is this clear? Yes? Is this clear?
Yeah.
So this p I can further write as psi inverse of x, right? So then I write everything in terms of xb. So this becomes A of psi inverse x into the column vector b. So this whole thing is a C infinity function of the pair xb in R2n. And this thing belongs to R2n. Okay. So this is a smooth map from R2n to R2n. It's a smooth diffeomorphism because the inverse will be just capital phi inverse composed with phi, which will have the same form. Okay, it will also be a smooth map from R2n to R2n. Is this clear? Yes? Okay.
Yes, sir.
All right. So we have these charts, capital phi, let's say, which goes from pi inverse u in Tm to phi of u cross Rn, which is sitting inside R2n. Okay. And now this map, okay, so now we have to be a bit careful. Actually, on Tm, I did not define a topology yet, right? Tm is just a set. So this map I know is just a bijection. This is just a bijection. But using this bijection, I can define a topology on Tm, right? So you say that you just have to define a basis of neighborhoods of each point, right? So basis of neighborhoods of a point PV in pi inverse u. You define this to be phi inverse of a basis of neighborhoods of phi of PV in R2n. All right. So you use this map capital phi to define a basis of neighborhoods here. Now, this is independent of the choice of chart capital phi, because if I chose another chart capital psi, then the change of charts is a smooth map from R2n to R2n. In particular, it's a homeomorphism. So the basis of neighborhoods using capital phi will also be the same as the basis of neighborhoods using capital psi, right? Because the change of charts is a homeomorphism of R2n to itself. Is it clear? Yes? Is that clear?
Yes, sir.
Okay, so that means that you can define a topology and then it's not hard to check. This topology will be second countable and Hausdorff. Okay, so you try and verify that. It's not hard to see. And then once you define this topology, then by definition, with this topology, capital phi will become a homeomorphism, right? Is it clear? By definition, capital phi will become a homeomorphism, right? Because it will take neighborhoods here to neighborhoods here. So, right? So then the capital phi's become homeomorphisms, so such that the change of charts is smooth. So therefore, Tm becomes a manifold, all right? Of dimension 2n. Okay. Is that clear? Yes?
Yes, sir.
Okay. Yeah, so okay, good. So finally we've got that the tangent bundle itself is a smooth manifold of dimension 2n. Okay. So look, if this all seems kind of abstract, then let me just give you a concrete example. If you look at the tangent bundle of S2, that is pretty easy to write down as a manifold of dimension 4. So at each point, what will the tangent space look like? If I take a point P on S2, this tangent space TPS2, this tangent plane to the sphere at this point is nothing but the orthogonal complement of P, right? You know that the radius vector is perpendicular to the sphere at each point, right? So this you can identify with P perp sitting inside R3, right? This is a two-dimensional subspace of R3. Is that clear? Yeah. So the tangent bundle of S2, T of S2, this you can identify actually with a subset of R6. This will be the set of pairs P comma V in R3 cross R3, where P belongs to S2. So norm P is 1. Okay. And V belongs to P perp. So inner product PV equal to 0. That's it. Okay. Is this clear? Yes?
Yes.
Okay. So this is a concrete example of a tangent bundle. All right. So this will be a manifold of dimension 4. Okay, you can see that intuitively because on this P comma V, this is in R3 cross R3, which has 6 dimensions, but we're applying 2 constraints, right? So one is that norm P is equal to 1. That's one equation. And then we have inner product PV equal to 0. That's another equation. So that should cut down the dimension by 2, right? So 6 minus 2 is equal to 4. Okay. All right. I mean, where are the 4 dimensions coming from? P can move in locally in 2 dimensions, and V is moving in a 2-dimensional vector space P perp, right? So 2 plus 2 is also equal to 4. Okay. Is that all right? Yeah. Yes, is this clear? Yeah. Okay. Okay. So next we want to talk about what are vector fields on manifolds. So these will be very important for us throughout. So a vector field means that at each point of your manifold, you will be choosing a tangent vector, okay, which varies in a smooth way. So for example, you could have a vector field which points along. So we talked about vector fields in Rn. So there at each point in Rn, you had a vector in Rn. Now at each point in the manifold, you have a vector in the tangent space at that point, right? So for example, you could have a vector field like this. And just like we talked about integral curves of vector fields in Rn, similarly, we'll be talking about integral curves of vector fields in a manifold. So those will be curves which will be tangent to the vector field. Intuitively, you get them by joining the arrows here. So in this example, the integral curves will be longitudes, okay? Going from North Pole to South Pole. Okay. So what is the formal definition? So let's get back to the notes. Okay, so we don't have much time. I'll just finish by saying this. So a vector field on an open subset of M, this is a smooth map X from the open subset U in M to the tangent bundle Tm, such that at each point P, X of P belongs to the tangent space at P. Okay. All right. So X of P belongs to TPM for all P and U. So X being smooth just means that in the charts, right, the X should be a smooth map with respect to these charts on TM. So that just means smooth means that basically the coefficients of del del xi which come here, the AIs, these should be smooth functions of P, right? So see, the vector field X I can write as at each point as a linear combination of the basis vectors del del xi, right, on a chart. So locally X I can write as a sum of del del xi's with coefficients AI's which are functions. So the vector field X will be smooth as a map to the tangent bundle, as a map between manifolds, if and only if all the AI's are smooth functions. Okay, the coefficients of X with respect to the basis del del xi's, these are smooth functions. Okay. And we will be using this notation, chi of u is the space of smooth vector fields on U. Okay, so this is a vector space because I can add vector fields pointwise, right? Since, I mean, for two vector fields X and Y, XP and YP are vectors in the same tangent space. So I can add them, look at XP plus YP, okay? All right, so we'll talk more about vector fields next time. Let me stop for today. If there are any questions, I can do another session for 5-10 minutes if there are any questions. If not, let me stop. So are there any questions? Okay, so let's stop today. We'll continue on Friday. Okay.